thanks for coming. There's not much more to do other than introduce Avi. We only met like 6 or 8 months ago, but he had an awesome company called DabbleDB that got bought by Twitter, and now he's at Etsy. DabbleDB was such a cool thing. I was so sad to discover it only after it was acquired. But he's going to talk to us about abelian sets. Is that how to pronounce it?
Oh, abelian, yeah.
Abelian.
Groups.
Abelian groups, sorry.
But not really.
But not really. But yeah, I mean, it's pretty informal. You should know that Kickstarter's hiring. Go to kickstarter.com/jobs. That's the promotional part of this evening. But without further ado, Avi, Brian, thank you.
Hey. I'm too lazy to make slides, so this is going to be a whiteboard talk. And also, I have a very pro-heckling policy. So, you know, if anyone wants to... Yeah, if anyone wants to shout anything out in the middle and completely derail me, that will probably make it a better talk, so I welcome it. So I'm going to talk about adding things. The inspiration for this talk was my friend Steve, who's a mathematician, tweeted this ridiculous thing that was like, if you're building analytic systems and you don't know what an abelian group is, then just stop. And he's completely wrong. He's completely wrong, but there is a kernel of truth to it, which is that abelian groups and other things in abstract algebra that those of us who do not have math backgrounds usually do not know what these things are, provide a really useful framework for thinking about some of the practical problems of building software systems for aggregation and analytics. And so, you know, what I think actually is that if you build an analytic system and you know what you're doing, then you do know what an abelian group is, you just don't know it by that name. And so what I'm going to try to do is talk about, you know, a little bit about what this mathematical framework is, but more to the point, you know, why this is a useful way of thinking about things. But it really does start with just adding things. And so I'm going to go through, the first bit of the talk may seem like what I'm saying is obvious, and that's okay. Because the point is that, you know, the obvious things, there's lessons in the obvious things that we can apply to the less obvious things. So, you know, some of you may be familiar with a system that actually came out of Etsy called StatsD, and StatsD, if you know what it is or you don't know what it is, it doesn't really matter. Yay, StatsD. But at its simplest, StatsD is a way to count things. And so let's say that you are an e-commerce site and you have transactions coming in, and you want to know how much money you've made at any given point so far. And so you might have a line in your code that looks something like this. If I need to write bigger or something, someone tell me. StatsD.increment, and let's call this revenue. And then I'll have like order.value. Something like that, whatever, it doesn't really matter. The point is, your application is generating a bunch of calls of these things, and so what you end up with is a stream of order values coming into some system, and all that system is supposed to do for now is give you a total, right? We want to know how much money we've made. So, okay, so let's say we've got a bunch of order values coming in. We've got $4, $8, $15, $16, $23, $42. Anyway, yeah, some people are lost by those numbers, but Eric gets it. So you've got the stream of numbers coming in, and what is the algorithm that we are going to use to come up with a total? Well, again, I said the first part was going to be kind of obvious, right? There is an easy, obvious algorithm for keeping this total, and it's going to look something like this. We're going to start out by saying revenue equals 0. And then we're going to say something like, in pseudocode, you know, for value in, you know, stream, revenue equals revenue plus value. End. Okay, so this is a very simple algorithm, and that's good, right? Because it's easy to understand, it's easy to implement. And what are we actually doing when we do this? So we are adding up all of these numbers, and we're adding them up in this order, right? So we start with 0, So I should put a 0 here. And we're doing 0 plus 4. Okay? And then we're taking that result, and we're adding 8. And then we're taking that result, well, I'm going to run out of space for parentheses here, and we're adding 8. And you kind of get the idea, right? Okay. And then this all adds up to whatever it adds up to, I don't remember. Okay, fine, great. Now, in Stats D, and in general, you don't just want to know the total, right? You want to know what was the total for this minute, and what was the total for that minute, and what was the total for that minute. And so actually what you're going to do is, in this code, you're going to occasionally like flush revenue to disk, whatever, right? You're going to write down what was the revenue at this point, and you're going to reset it to 0. And so you're going to end up with something that kind of looks like this instead. You're going to have like minute 1, I had 0 plus 4 plus 8. And then let's say like this is the next minute, right? Minute 2 is 0 plus 15 plus 16, and so on. You get the idea, right? And there might be some minute, incidentally, where nothing happens. So we're going to have minute 3, and that's going to be 0, right? Okay, fine. So far, so good. But now you might also want to know the total. So, okay, we could be separately keeping track of the total, but actually there is something cool about adding numbers up, which is that if I have these subtotals, right, so I've got like this is 12, and this is like 31, and this is 0, and I want to know the total, I just add up the subtotals, right? So what I'm actually storing, right, is not these numbers. I'm just storing the subtotal for the minute, right? So what I'm actually storing is not this. What I'm storing is 12, what I'm storing is 31, what I'm storing is 0, but now I want to know the total, and I can be like, oh, okay, right now, at this point in the stream, the total is 43. Okay, so that's cool. I'm assuming you are all still with me through this very complicated math. Okay, well, so let's say that we get so massive, please, that one machine is not enough to add up all of these numbers, right? It can't keep up. And so we have to split this stream over multiple machines. So let's say, sort of for the sake of argument, that like even numbers go to one machine and odd numbers go to the other machine, or whatever. It doesn't really matter, right? Oh, I should say, by the way, that like, you can think of what you're doing here as just like a re-parenthesization, if that's a word, of this, right? So we sort of had like, kind of put in some extra parentheses, right? But it still works, because that's the cool thing about plus, is that like you can re-parenthesize all you want and you still come up with the same answer. And if we split them in separate machines, I won't go through all the mechanics of it, but you can kind of imagine that when we want the total, it's sort of like we're also just reordering everything, right? So, if what we have is we have, I'm running out of space, let me erase some stuff.
Get you some chalk. There's chalk if you...
Can people see the chalkboard too? I can move to the chalkboard. So, if one machine gets, I said even odd, yeah, sure, why not? So one machine gets 0, 4, 8, 16, thank you, 42. The other machine gets 0, 15, 23. Okay, so if you wanted to total them up, the efficient thing to do, right, is to get a subtotal on each machine and then just send the subtotals to one central place and total them up, right? And so now, again, we're still adding up the same numbers, but we're doing it in a different order. And so we end up with something that looks like, 0 plus 4 plus 8 plus 16, blah, 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 plus, right? And then we have this other big parenthesized thing that is the other machine, right? And because it is addition, it still works. Okay, great, fine, fine, fine. So, StatsD is not just about counting things. There's another thing that is cool that StatsD does, which is you might want to time a piece of code. And you might want to know, let's say for the sake of argument, the longest amount of time that that ever took, right? So this is a useful performance metric. And so the code for that looks similar, but instead of saying increment blah blah, you might say like, I don't know, time, response time, some number of milliseconds, whatever, right? But what it wants to do is to keep a maximum of this. So, oh my god, now we have to implement this whole other thing. What's the code for that going to look like? Well, we're going to start the maximum at 0. for value in the stream, the maximum is the current maximum, and whatever, I'm going to make up some operator that means max, max with the value. So for each minute, we keep the maximum for that minute. And how do we compute the total maximum? Well, we can do it. We can take the sub-maximums, or whatever you want to call it, and max them all together using actually almost exactly this algorithm again, and get the total maximum. Well, what if we partition it across a bunch of machines? Well, actually, the same thing happens, right? We can take the maximum that each machine has and max all of those together, and we still get the maximum. So that's cool. That's great. We're on a roll. Let's do the minimum. So we start setting it to Our attempt at abstracting this into some great framework has just failed. Almost. Because this is where my friend Steve comes back and says, oh, obviously all you need is a commutative monoid. I mean, you guys all knew that, right? But he's not crazy. And he's not crazy because if you go to Wikipedia and you look up what is a commutative monoid, this is what it will tell you. It will tell you a commutative monoid is something where you have a set, let's say the integers, for example. And you have an operation on that set that takes two of those things and produces another of those things. So plus is this, it takes two integers and produces an integer. Max is also this, it takes two integers and produces an integer. Min is also this. And you have to have a third thing, which is an identity element. And the identity element in the set is the one where if you take something, one member of the set, and you apply the operation, let's say plus, to the identity element, the left is something, the right is the identity element, let's say 0, you end up with the same thing, the thing you had before, right? So 3 plus 0 is still 3, right? The max of 3 and 0 is still 3. And so, maybe if we can come up with an identity element for min, then we can reuse all of this code still. And we can. So the identity element for min is infinity. Or max int or whatever, right? So all that changes here, we just have to change one more bit of our code, which is we don't initialize things to 0, we initialize them to inf. And all of our code that we've written will already work. And so it turns out that, sorry, I forgot an important property of these operators. So to be a monoid, it has to be associative, which if you all remember high school math, means that basically you can reparenthesize it however you want, right? So that's true for addition, that's true for max, that's true for min. And it has to be commutative, which means that you can flip the order around and it still works, right? So sorry, a monoid has to be associative, a commutative monoid has to be commutative. Anyway. So cool. So this architecture that we've just described, this algorithm that we've just described, will work with anything that is a commutative monoid. So if that's just summing and maxing and minning, that's maybe not that exciting, right? But it turns out that there's an incredible number of things that are commutative monoids, and that you can then plug in with this same code, the same test framework, the same architecture, these same efficiency expectations, and so on, and it will work. So, what are some of those things? Well, we've done max, min, and sum. How about mean, right? Average. So, it seems at first like this is not going to work. Because if we take a bunch of sub-averages, right, we take the average for minute 1 and the average for minute 2, and we try to average those, we're going to get the wrong answer. We're almost certainly going to get the wrong answer, right? And so you have to stretch things a little bit and say that, well, really what you have to do, remember that monoids, that these structures take a set. So we're no longer dealing in the set of integers. We can no longer just say that we're going to keep in integers these elements. Instead, we're going to keep a pair of things, right? What we're going to do for average is we're going to keep the average and we're going to keep the count. And now we can combine them, right? If we write code that knows how to do plus on this, then we can have subtotals that have the sub-average and the sub-count, and we can combine them. Yes, Fred?
Just to heckle. You can't take an average of an average, but you can if you have the count, because then you can balance it out as a weight.
Right.
Just to be clear.
Right. So thank you. So I wasn't being clear enough, right? So with the count, it is possible to combine two averages because you know how much to weight the one average or the other. You can also equivalently keep a sum in a count, right? And then you can drive the average easily by dividing, right? So that's good. It turns out that actually sort of all of the statistical moments, which is the sort of fancy name for things like averages and standard deviation, and then you get into like skew and kurtosis and so on, can be kept that way. So that's cool. It's good that you can do that. What else can you do? Well, you can do histograms, which is kind of cool. So what do I mean by that, right? So if I have a map, basically, or a hash, where I've got like some key x, and then some number, and then some other key y, and then some number. And let's say I've got another one that's like x goes to 2, and then nothing else. I can add these, right? And my plus operation is going to do now x is 3. Can people see this? Y stays 3, I guess, right? And so that ends up basically being a histogram. But the cool thing about this is that it's recursive. So what do I mean by that? Well, our values here in this hash table were numbers, were integers, and the operation we applied when combining these was plus, right? But I could also have a hash table of averages and combine them using the way that we know how to combine averages, right? And so, you know, you can start plugging in. Once you have things you can add in a generalized way, you can start plugging all of these in. Okay, so what's some more fun things that we can do still? So we can do, let's say we want to find the top 10 response times we've ever seen, or whatever, right? So that's also, you know, we're in a new set here where the things that we're keeping track of are now lists of 10 numbers. And the way that we add them is that we combine the left list of 10 numbers and the right list of 10 numbers and union that set, basically, and then take the top 10 resulting, right? But it's so, you know, this is a very different thing from what we started out with, which was like adding counts. Now we're keeping top 10, but actually the code and the architecture looks exactly the same for doing that thing. So, you know, what's something else that we might want to do? What's something else that StatsD does?
Gauges, unfortunately. 90th percentile.
Yeah, 90th percentile is really hard, and I can get to that, but it would take a lot of math. Another one that's hard that I was hoping you were going to say, I should have planted you, is unique visitors, right?
Yeah, that's hard.
Unique visitors is hard. And in fact, you cannot get an exact answer to unique visitors with this, but you can get an estimation. There's lots of ways you can get an estimation, but there's one way that you can get an estimation that I think I can actually explain. And so let me try to explain it. So yeah.
Before you start, can you explain why you can't get the exact one?
Yes, right. So with unique visitors, right, what you would do to get an exact answer is you would have to keep a list of all of the visitors, all of the visitor IDs, let's say, that you'd seen, right? And you know, every time you go to add a new visitor, you'd have to check, is it already in the list? And if it's already in the list, then you don't want to increment the counter or whatever, right? So you can do this, but the problem is that that list keeps growing and growing and growing and growing, which kind of screws up the architecture that we're describing here, right? Because, you know, we want these distributed machines and we want to be like recording the values every minute or whatever. We don't want these to be big values and like unbounded values that we're sending around. We want a bounded counter, right? And so we can't do an exact unique visitors, but we can do a really good estimate, and I'm going to show you how. So let's say that every time a new visitor ID comes in, so I've got this stream of visitor IDs, A, you know, B, C, D, E. Okay. Every time when a new visitor ID comes in, or a visitor ID comes in, I don't know if I've seen it before, right? I hash it using a good hash function to a number between 0 and 1. Okay? So all of these get turned into floating point numbers. So this becomes like 0.1, 0.3, 0.35, whatever, right? And this is a hash function, so the properties that we want are obviously the same visitor ID has to hash to the same number every time we see it, right? And we want these to be uniformly distributed over 0 to 1, right? So, okay, let's think about the number line between 0 and 1. So, I start out with just like one visitor comes in, and I like get a mark on my number line there, right? Another visitor comes in, another visitor comes in. The first one comes back again, and you know that's going to be another mark on the number line in the same place, right? So my number line kind of fills up with as many marks as I have unique visitors. Okay, question. This is between 0 and 1. I have 100 unique visitors. What's the average distance between any two marks on this line that are next to each other? So they're uniformly spread over 0 to 1, right? There's 100 of them.
0.01.
Right, so on average, there's 0.01 between each of these, okay? And that average is going to be true anywhere on the number line. So let's say we just keep the top, whatever, 10 of them, right? And we look at the average distance between those 10, that's still going to be 0.1. So if we know that the average distance is 0.1, then we know that we have 1 over 0.1, which is 100 unique visitors. And can we in our architecture deal with a top 10 numbers? Well, yeah, we just talked about that actually, right? You know, you can do a top 10. And so you can keep this top 10 list, and whether it's 100, 1,000, basically the more you add, the more the top 10 is going to get squished up near the top of the number line, and so you're going to be able to tell just by looking at that, or estimate how many unique visitors you have, right? And yes?
Sorry, so because you can make the assumption that they're uniformly distributed across the range.
That's right, because your hash function guarantees that.
Right, so in a sense you're kind of sampling a part of the range and extrapolating
the fact that it's the top is irrelevant, right? It can be the top, actually traditionally it's the bottom, but the point is you have a way to easily and sort of consistently sample from some section of this range, right, without keeping the whole thing.
And that could be on one machine.
Yeah, well, so you keep that for every minute, or you keep that for every day, right? And that was actually the next point I was going to make, right? Is that, remember, these things add, right? So if you keep this thing, which is these like top 10 hash values for every day, and that gives you, each of those individually gives you the estimate for how many unique visitors you had that day, but now you add those all up and take the top 10 from adding those all up, and now that gives you, for a month or whatever, right? And now that gives you unique visitors for the month very, very quickly, right? So you just throw in Memcache or whatever somewhere, right, one of these data structures for each minute or each hour, each day or whatever, right?
Isn't that only counting the unique people within that minute though?
It's counting the unique people within that minute, but if you take that and you combine it with the unique people from another minute, you actually get an accurate estimate of the union of that set, right? Of the uniques across that 2 minute range. It's not like adding, I had this many uniques then and this many uniques then as like a simple like numeric sum, right? These things actually combine. And if you think about it, it makes sense because it's sort of like you're just combining those streams.
It kind of averages,
right?
In a way.
So that's really the important thing about this, right? Is that it gives you an efficient way to compute things like unique visitors, and actually, it can be really efficient. And this is kind of fun. We're talking about minutely data, right? Let's say that we kept this thing for each minute, right? So it's like unique visitors for this minute, this minute, this minute, this minute, this minute, this minute, this minute. Okay, and I want some like very large range of these. This is actually still going to be kind of slow because I'm going to need to pull from my database these like whatever very large number of these and then combine all of them, and it's doable, but it's a little bit slow, right? Let's say that I also keep one for every 2 minutes. Let's say that I also keep one for every 4 minutes. Let's say that I also keep one for every 8 minutes, every 16 minutes, every 32 minutes, right? This like gets down to a tractable number pretty quickly, right? And now I want this range. Let me sort of, this drawing is not great, but hopefully you can kind of see what I'm talking about. Now I want to do this range, right? Well, this range is just like this plus this plus this, right? So by doing these, like keeping these like power of 2 roll-ups, right, you can end up, and it ends up being that it's like max of 2 log 2 of the size of your range, retrievals and additions that you need to do, right? And again, you can do this for anything that falls into this structure of things that kind of feel like adding, right? So maxes, mins, top n, unique values, histograms, stochastic gradient descent, combining affine functions, min hash similarity estimates, etc., etc., etc. Count, min, sketch, frequency estimates, etc., etc., etc. There are a truly surprising number of things once you think in this framework that can be computed roughly in this way. Yes?
If you're only looking at the top 10, how do you account for the variance in your estimate? And then if you're aggregating, you can't aggregate your variances, right?
So there is error. The error does not depend on the, I do not believe the error depends on the size of the stream for this estimator, right? So your variance, this is unintuitive that this is true, and I'm not going to prove it right now, but the variance does not actually increase as you aggregate them. And to give you, what's that?
It depends more on the hash function.
It certainly depends on having a good hash function. It also depends primarily on how many, like top 10 is much worse than top 100, right? You know, the sort of state of the art in this kind of algorithm, this kind of probabilistic distinct value estimation, is not what I just described, which is k-min hashes. It's something called hyperlog-log, which is similar, but I cannot explain on a whiteboard to you. Maybe somebody can. But the kind of rule of thumb that I remember for that is that if you're willing to allocate 1K of RAM for each counter, you get about 2% error. And it doesn't matter, that's whether there's like 1,000,000 distinct values or 1,000,000,000 distinct values, right? You're still going to get 2% error if you're willing to give it a K per counter. Which strikes me as pretty good, like surprisingly good, right? Again, I don't have anything else to say. That I would like to take questions, but I realized last time I gave this talk that, given this whole talk without actually mentioning what abelian groups are. So almost as a footnote, what I've been describing is commutative monoids. An abelian group is the same thing, but where you also have an inverse, or equivalently a subtraction operation, right? So some of these things, like totals, you can subtract. Some of them, like max, for example, you can't subtract, right? If I tell you I've got the max, and but I want to subtract 3, actually wait, does that work? It doesn't work. No, it doesn't work because if my max is 3 and I want to subtract 3, now I'm screwed, right? Well, what was the next max? I don't know, right? I've lost it. I've already thrown it away, right? Do you care about subtraction? Sometimes you care about subtraction, right? So it would be nice if this stream of transactions that we've got all of these aggregates on, one of the transactions gets reversed, and now I just want to incrementally update like everything that I've computed. So for things that are abelian groups, rather than merely being commutative monoids, I can do that because I have subtraction available to me. And usually you think of it as actually just being a way to invert something, right? So I've got this transaction, I've got the normal thing I would be adding for it, I'm going to invert it and then add that onto the stream, make it negative basically. So for some things that works, for some things that doesn't, but it's important to know that when you're thinking about these systems. Really the monoids are more important.
It's interesting, abelian groups are interesting because they're non-associative, and that's like a...
No, they are also associative. Okay. So they are everything that a commutative monoid is, but also have this subtraction-like thing. right? Then you get into like rings which have multiplication and blah 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 blah. But yeah.
It's not really subtraction though. It's not a different operator. It's just.
That's right. It's not a different operator. It is simply a way to invert something into
Right,
its
so
like
if
negative
If
form.
you're adding, say, take the group like mod 12 clock arithmetic.
Yeah.
You add 2 and 3, you get to 5. Well, there should be another operator which can get you back to 2.
Right.
Which would be 9, right? No, 7. No, that was right the first time. 9.
Right, right. So you can invert it under that like mod 12 group. You can
And the
invert
problem
it.
with max is if you take the max of 3 and 5, you get 5. But
Yeah.
there's nothing you can take the max
invert
with
that.
5 with to get back to 3.
3. Yeah, exactly. Exactly. Thank you. So yeah. So in practical terms, by the way, if you happen to be a Scala hacker, there's a project at Twitter that I've also contributed to called Algebra that implements sort of this framework and also a very large number of useful implementations of sort of analytics-oriented monoids and groups and rings and so on. So for some people that's completely useless, but for some people the fact that there's good Scala implementations of this might be interesting, so I'll point that out. And Twitter uses it both in like a MapReduce context, which I actually probably should mention, right, that my like distributed context lends itself perfectly to implementation on top of MapReduce, right? So, you know, you would have your mappers do this, your mappers or combiners would do a sort of initial aggregation on the map side, you would shuffle all those to the reducers, finish the aggregation using the same operators on the reduce side and get an answer, right? So Twitter uses it both for MapReduce, but then also for streaming using Storm. You can use exactly the same code, but in a streaming context, you know, you basically want to do the same things, and so that's cool and useful, right? So if there's any questions that weren't Fred shouting at me in the middle of the talk,
You asked for a heckle.
I asked. Yeah.
On the unique operator,
Yeah.
or the unique visitors, when you're taking the top 10, isn't it pretty expensive to do a sort on all of the...
Well, so two things. One, it's not that expensive to do a sort when you have a small number of items, right? So if you're literally taking the top 10 to combine and then sort is not that bad. But also, if you keep them sorted, right, then combining two sorted lists into a third sorted list is actually in linear time, right? Because you just walk through both of them kind of in parallel. Or you can think of it as like you keep a heap, right? And then you also get very good performance inserting. So no, actually it doesn't, I mean, it's still effectively an order 1 operation.
I was going to say, compare that to take a fixed amount of space between it, so from 0 to 0.1, and then count the number of things in there, rather than taking a number of things and seeing how much space they take up. It's the same operation.
The problem with doing that is that that gets more expensive. You need more space, because you need to actually store the unique things, not just the number of things, so that when you combine two of them, you knew when there was duplicates, you knew when there was intersection, right? And so then you need to take more and more space to store that list of things as the number of items in your stream gets larger, whereas this is fixed in both space and error, no matter how big your stream is, right? John?
Yeah, so this will get me back to your hash example with the monoid.
Yeah.
So I think I mentioned this before once. I'm trying to still wrap my head around how this is distinct from the series type in pandas. Maybe this is an unfair question because you've never used it.
I haven't, but...
Okay, so series has at minimum these operations. I guess the question to me is whether or not it has other operations or is entirely expressible as basically a hash with a monoid.
Yeah, so
the whole trick with this thing, is exactly like, I want to label a vector with things like, this is the stock price for Apple.
Right.
This is the stock price for Apple. And whenever I do additions, I want to make sure that the Apple things get added together.
Oh yeah, that's totally like the map monoid. Yeah. And actually, so there's a patch for Julia after Stefan came to see an earlier version of this talk that's like, oh, okay, map should operate more like monoids. So, yeah. Any other questions?
Should we assume that like all unique page counts or all unique numbers are using this?
Oh, that's a good question. I think these days, like hyperlog, which is sort of the like fancy better version of what I described, is pretty standard for doing like fast estimates of uniques. So probably they're using something like this. You know, this whole class of probabilistic data structures is very cool, and I could talk about them for a long time, but this probably isn't the right audience for it. But yeah, there's lots of good literature on this that you should look into. But yeah, I think right now hyperlog is the thing that you should assume everyone's using.
So,
Yeah.
the only other probabilistic data structure right now is Bloom filters.
Yeah,
Yes.
I was just going to ask that. I was like, compare
Bloom filters can be expressed in this framework. Algebra does have a Bloom filter implementation that comes in very handy. Count min sketch is another one that's very cool. Count min sketch is a way of estimating the frequency of items in your stream, right? And so you're not asking, does it contain this? You're not asking how many of them were there. You're asking how many times did I see like this refer, right? And there might be like a billion unique refers, so I don't want to just like keep a hash table of them, right? But I want to make sure that at least for the ones that are like a significant percentage of the stream, I get a pretty decent answer back, right, in a fixed amount of space. And it's pretty straightforward to use that to build a heavy hitters, which is, you know, give me anything above like 5% or anything above 1%,
So is
right?
the error rate on that one proportional to the distance from
The error rate on count min sketch is related to obviously the amount of space that you give it, and also a fraction of the total stream size. And so effectively it's a fixed error on the percentage, but, or you can think of it as this kind of sliding error on the count, right? But basically, like, if you give it enough space, you know, you can know that your percentage is only going to be a few % off. Does that make sense? Right? And then you can use count min sketch to get to percentiles. So that gets complicated. You have to use a tree of count min sketch estimators, and then you do this like binary search thing through them and range queries and blah, blah, blah. And I do not have time to explain it, but it's really fun to look up how it works. So yeah, that's another major one. Min hash is one I mentioned before, which is a probabilistic way of looking at the similarity of sets. So that gets really useful for like recommendation algorithms, for example. Those are the main ones off the top of my head that we have implemented. You know, there's others out there. But. Cool.
Well, thanks.
Anything else?